Inorganic compounds essential to human functioning. An inorganic compound is a substance that does not contain both carbon and hydrogen. A great many inorganic compounds do contain hydrogen atoms, such as water, H2O, and the hydrochloric acid, or HCl, produced by your stomach. In contrast, only a handful of inorganic compounds contain carbon atoms. Carbon dioxide, or CO2, is one of these few examples. An organic compound is a substance that contains both carbon and hydrogen. Organic compounds are synthesized via covalent bonds within living organisms, including the human body. Recall that carbon and hydrogen are the second and third most abundant elements in the human body. These two elements combine in the foods you eat, in the compounds that make up your body's structure, and in the chemicals that fuel your body's functions. Here, we will examine three groups of inorganic compounds essential to life: water, salts, acids, and bases. As much as 70% of an adult's body weight is water. This water is contained both within the cells and between the cells that make up the tissues and organs. Its several roles makes water indispensable to human functioning. Water is used as a lubricant and a cushion for the body. Water is a major component of the body's lubricating fluids. Just as oil lubricates the hinge on a door, water in synovial fluid lubricates the actions of body joints. And water in pleural fluids helps the lungs expand and recoil with breathing. Watery fluids help keep the food flowing through the digestive tract and ensure that the movement of adjacent abdominal organs is friction-free. Water also protects cells and organs from physical trauma, cushioning the brain within the skull and protecting the delicate nerve tissues of the eyes. Water cushions the developing fetus in the mother's womb. Water is also used as a heat sink. A heat sink is a substance or object that absorbs and dissipates heat, but does not experience a corresponding increase in temperature. In the body, water absorbs the heat generated by chemical reactions without greatly increasing temperature itself. When the environmental temperature soars, the water stored in the body helps keep the body cool. This cooling effect happens as warm blood from the body's core flows to the blood vessels lying just beneath the skin, where heat is then transferred to the environment. At the same time, sweat glands release warm water in sweat. As this water evaporates into the air, it carries away heat. Then, the cooler blood from the periphery circulates back to the body's core. Water is a component of liquid mixtures. A mixture is a combination of two or more substances, each of which maintains its own chemical identity. In other words, the constituent substances are not chemically bonded into new, larger compounds. The concept is easy to imagine if you can think of a powdery substance such as flour and sugar. When you stir them in a bowl, they obviously do not bond to form a new compound. The air that you breathe is a gaseous mixture containing three discrete elements: nitrogen, oxygen, and argon, and one compound, carbon dioxide. There are three types of liquid mixtures, all of which contain water as a key component. These are solutions, colloids, and suspensions. In order for cells to survive in the body, they must be kept moist in a water-based liquid called a solution. In chemistry, a solution consists of a solvent that dissolves a substance referred to as a solute. An important characteristic of solutions is that they are homogeneous. That is, the solute molecules are distributed evenly throughout the solution. If you were to stir a teaspoon of sugar into a glass of water, the sugar would dissolve into sugar molecules separated by water molecules. If you were to add more sugar, the ratio of sugar to water would then change, but the distribution, provided you have stirred it well, would still be even. Water is considered the universal solvent. and it is believed that life cannot exist without water because of this. Water is certainly the most abundant solvent within the body. Essentially, all of the body's chemical reactions occur among compounds dissolved in water. Because water molecules are polar, having regions of positive and negative electrical charge, water readily dissolves ionic compounds and polar covalent compounds. Such compounds are referred to as hydrophilic or water-loving. Nonpolar molecules do not readily dissolve in water and are considered hydrophobic or water-fearing. Various mixtures of solutes and water are described in chemistry. The concentration of a given solution is the number of particles of a solute in a given space. For example, oxygen makes up about 21% of atmospheric air. In the bloodstream of humans, glucose concentration is measured in milligrams per deciliter. A healthy adult individual averages about 100 milligrams per deciliter. Another method of measuring the concentration of a solute is by its molarity. Molarity is a concentration which equals the moles of molecules per liter. The mole of an element is its atomic weight, while a mole of a compound is the sum of the atomic weights of its components, called the molecular weight. An often used example is calculating 1 mole of glucose with the formula C6H12O6. Using the periodic table of elements, we can see that the atomic weight of carbon is 12.011 grams, and there are 6 carbons in glucose, for a total atomic weight of 72.066 grams. Doing the same calculations for hydrogen and oxygen, the molecular weight equals 180.156 grams. This is the gram molecular weight of glucose. When water is added to make 1 liter of solution, you have a 1 molar solution of glucose. This is particularly useful in chemistry because of the relationship of moles to Avogadro's number. A mole of any solution has the same number of particles in it. This magical number, called Avogadro's number, is 6.02 times 10 to the 23rd power. Many substances in the bloodstream and other tissues of the body are measured in thousandths of a mole, or millimoles. A colloid is a mixture that is somewhat like a heavy solution. The solute particles consist of tiny clumps of molecules large enough to make the liquid mixture opaque. This quality is due to the particles being large enough to scatter visible light. Familiar examples of colloids are milk and cream. In the thyroid gland, the thyroid hormone is stored as a thick protein mixture called a colloid. A suspension is a liquid mixture in which a heavier substance is suspended temporarily in a liquid, but over time settles out. This separation of particles from a suspension is called sedimentation. An example of sedimentation occurs in the blood tests that establish sedimentation rate, abbreviated SED rate. This test measures how quickly red blood cells in a test tube settle out of the watery portion of the blood known as plasma over a set period of time. Rapid sedimentation of blood cells does not normally happen in a healthy body, but aspects of certain diseases can cause blood cells to clump together. These heavy clumps of blood cells settle to the bottom of the test tube more quickly than do normal blood cells. 2 types of chemical reactions involve the creation or the consumption of water. These are dehydration synthesis and hydrolysis. In dehydration synthesis, one reactant gives up an atom of hydrogen, and another reactant gives up a hydroxyl group in the synthesis of the new product. A molecule of water is released as a byproduct. This type of reaction is sometimes referred to as a condensation reaction. In hydrolysis, a molecule of water disrupts a compound, breaking its bonds. The water is itself split into one atom of hydrogen and one hydroxyl group. One portion of the compound then bonds with the hydrogen atom, and the other portion bonds with the hydroxyl group. These reactions are reversible and play an important role in the chemistry of organic compounds. Salts are formed when ions form ionic bonds. In these reactions, one atom gives up one or more electrons and thus becomes positively charged, whereas the other accepts one or more electrons, becoming negatively charged. Salt can be defined as a substance that, when it is dissolved in water, dissociates into ions other than hydrogen ion and hydroxide. This fact is important in distinguishing salts from acids and bases. A typical salt, such as NaCl, sodium chloride, dissociates completely in water. The positive and negative regions of the water molecule attract the negative chloride and positive sodium ions, pulling them away from one another. These ions are also considered to be electrolytes because they are capable of conducting an electrical current in solution. This property is critical to the function of ions in transmitting nerve impulses and prompting muscular contractions. Many other salts are also important in the body. For example, bile salts produced by the liver help to break apart dietary fats, and calcium phosphate salts form the mineral portion of bones and teeth. Acids and bases. Acids and bases, like salts, dissociate in water into electrolytes. Acids and bases can very much change the properties of the solutions in which they are dissolved. An acid is a substance that releases hydrogen ions in solution. Because an atom of hydrogen has just one proton and one electron, a positively charged hydrogen ion is simply a proton. This solitary proton is likely to participate in chemical reactions. Strong acids are compounds that release all of their hydrogen ion in solution. In other words, the hydrogen ion becomes ionized completely. Hydrochloric acid, or HCl, is released from cells in the lining of the stomach. This is a strong acid because it releases all of its hydrogen ion in the stomach's watery environment. This strong acid aids in digestion and kills ingested microbes. Weak acids do not ionize completely. That is, some of the hydrogen remains bonded within a compound in the solution. An example of a weak acid is vinegar or acetic acid. A base is a substance that releases hydroxide in solution, or one that accepts hydrogen ion already present in solution. The hydroxyl ions, also known as hydroxide ions, combine with hydrogen ion present to form a water molecule. In doing this, they remove the hydrogen ion and reduce the solution's acidity. Strong bases release most or all of their hydroxide ions. Weak bases release only some hydroxide ions or absorb only a few hydrogen ions. Food mixed with hydrochloric acid from the stomach would burn the small intestine. To prevent this, the body releases bicarbonate, which is a weak base that attracts hydrogen ions. The concept of pH. The relative acidity or alkalinity of a solution can be indicated by its pH. A solution's pH is the negative base 10 logarithm of the hydrogen ion concentration within the solution. As an example, a pH 4 solution has a hydrogen ion concentration that is 10 times greater than that of a solution with a pH 5. In other words, a solution with a pH 4 is 10 times more acidic than a solution with pH 5. The pH scale consists of a series of increments ranging from 0 to 14. A solution with a pH of 7 is considered neutral, neither acidic nor basic. Pure water has a pH of 7. The lower the number below 7, the more acidic the solution, or the greater the concentration of hydrogen ions. The concentration of hydrogen ions at each pH value is 10 times different than the next pH. For example, a pH of 4 corresponds to a proton concentration of 10 to the negative 4 molar or 0.0001 molar, while a pH value of 5 corresponds to a proton concentration of 10 to the negative 5 molar or 0.00001 molar. The higher the number above 7, the more basic or alkaline the solution is, or the lower the concentration of hydrogen ions. Human urine, for example, is 10 times more acidic than pure water. The HCl is 10 million times more acidic than water. Buffers. The pH of human blood normally ranges from about 7.35 to 7.45, although it is typically identified as a pH of 7.4. At this slightly basic pH, blood can reduce the acidity that is resulting from carbon dioxide constantly being released into the bloodstream by trillions of cells in the body. Homeostatic mechanisms, along with exhaling carbon dioxide while breathing, normally keep the pH of blood within this narrow range. This is critical because fluctuations either too acidic or too alkaline can lead to life-threatening disorders. All cells of the body depend on homeostatic regulation of acid-base balance at a pH of approximately 7.4. The body, therefore, has several mechanisms for this regulation, involving breathing, the excretion of chemicals in urine, and the internal release of chemicals collectively called buffers into body fluids. A buffer is the solution of a weak acid and its conjugate base. A buffer can neutralize small amounts of acids or bases in the body's fluids. For example, if there is even a slight decrease below 7.35 in the pH of a body fluid, the buffer in the fluid will act as a weak base and bind the excess hydrogen ions. In contrast, if the pH rises above 7.45, the buffer will act as a weak acid and contribute hydrogen ions. Excessive acidity in the blood and other bodily fluids is known as acidosis. Common causes of acidosis are situations and disorders that reduce the effectiveness of breathing, especially the person's ability to exhale fully, which causes a buildup of carbon dioxide and hydrogen ions within the bloodstream. Acidosis can also be caused by metabolic problems that reduce the level or function of buffers that act as bases or that promote the production of acids. For instance, with severe diarrhea, too much bicarbonate can be lost from the body, allowing acids to build up in the bodily fluids. In people with poorly managed diabetes, acids called ketones are produced as a form of body fuel. These can build up in the blood, causing a serious condition called diabetic ketoacidosis. Kidney failure, liver failure, heart failure, cancer, and other disorders can also prompt metabolic acidosis. In contrast, alkalosis is a condition in which the body and other bodily fluids become too alkaline or basic. As with acidosis, respiratory disorders are a major cause. However, in respiratory alkalosis, carbon dioxide levels fall too low. Lung disease, aspirin overdose, shock, and ordinary anxiety can cause respiratory alkalosis, which reduces the normal concentration of hydrogen ions. Metabolic alkalosis often results from prolonged severe vomiting, which causes a loss of hydrogen and chloride ions as the components of hydrochloric acid. Medications also can prompt alkalosis. These include diuretics that cause the body to lose potassium ions, as well as antacids when taken in excessive amounts, for example, by some women with persistent heartburn or an ulcer. Thank you for watching.